Okay, welcome back. Let us take that continue from whatever we have said last time. We have seen the kind of effects that control the stereochemistry of a molecule. Especially we are looking at molecules where the axial orientation is preferred. Alkyl ketone effect is one, the anomeric effect is the other, and another is the allylic strains that pushes the groups in the axial orientation. Now, let us it means a reaction, okay. Something is happening to the molecule, that means the reaction. So, when a reaction occurs in a molecule or when a molecule reacts, it has to go through either a series of steps or it could be a one step reaction, whatever it may be. Every step has a transition state to be crossed. Okay. Every step has a transition state to be crossed. Now, you know that the slowest step of all the steps is the rate determining step, and if it happens to be only one step, then that has to be the rate determining step. Okay. Now, the stereoelectronic effect is the one which is such that the molecule when a transition state is created, the molecule, the orbitals, not the molecules, the orbitals that are, see, when a reaction happens to a molecule, not all parts of the molecule are affected, certain parts of the molecule are affected. That means, certain orbitals associated to that part, molecular orbitals associated to that part will be affected. Okay. Now, these orbitals which are affected, they will be in such a orientation, they will take up such a geometry in relation to the other the attacking species such as the nucleophile. So, nucleophile has an orbital filled with electrons and it is attacking a carbon, suppose, which is having a leaving group attached to it. Now, the transition state will be such, the system will adopt a transition state in such a way that the orbitals are aligned in 3D space, so that to give the maximum stability, that means to give the maximum overlap, or in other way around, stereoelectronic effect demands that in the transition state there should be maximum overlap of the orbitals that are interacting during the reaction. Okay. Now, let us show these slides and come back to the board later on. Now, when two orbitals combine with each other, that generates two atomic orbitals combine with each other, that generates two molecular orbitals. One is called the bonding scenario, when the two orbitals are in phase. So, the energy goes down and the system is stabilized. So, that is called the bonding scenario, and the other is when the orbitals are in opposite phase, then it goes up, they are mismatched and the energy goes up. So, there is practically no overlap because they repel each other, there is no overlap, and that is called an anti-bonding scenario. So, whenever two bonding orbitals interact with each other, there will be atomic orbitals interact with each other, there will be two molecular orbitals, one will be bonding and another goes up, that will be called anti-bonding. Okay. So, how does they look? Like if you have a sigma bond, carbon sigma hydrogen bond, CH bond, not hydrogen bond, CH bond. So, the hydrogen s orbital and the carbon sp3 orbital, they interact with each other and it looks like this. However, this is not the correct picture. I think there should be a tiny amount of space available here, which so what I am saying that actually it should be, sometimes we overlook this, but there is a tiny amount on this side also. This is the sigma, CH sigma. Okay. Now, similarly, you have CH, you have the C double bond. So, when two p orbitals are combining laterally, so what will happen? There are two scenarios that can happen. One is that they are in phase, just like this situation. So, they will combine with each other. So, there will be an electron cloud at the top and at the bottom. Okay. This is the bonding pi orbital. So, what is the anti-bonding pi orbital? The anti-bonding pi orbital, when they are in opposite phase, you see this phase is not matching with the top phase of this. So, they will repel each other and it will look like this, as if they are bending away from each other. So, this is the pi star orbital. And what is the sigma star orbital? When when these orbitals, so sigma star orbital is when the carbon has this orbital which is in say the plus phase and the hydrogen is in the minus. So, they are not in the same phase, then actually the combination will lead. So, this will go back to here. So, that means a bigger lobe on the back side and a very small lobe on this side. So, this is, and the hydrogen will also be deformed a little bit. So, this is the sigma star CH. Okay. So, that has got a bigger lobe on the back side of the hydrogen. So, that is what is shown here. Okay. So, if you, this is actually carbon chlorine. So, you have the sigma star, a bigger lobe on the back side. Okay. That is usually the antibonding orbitals are empty, because when two atomic orbitals combine, each usually have one electron, and then so both the electrons go to the bonding level and the antibonding level becomes free. Okay. So, that is the starting point, and out of these there is a concept which is called lowest unoccupied molecular orbital. That means, out of these there will be a set of antibonding orbitals and then there will be a set of bonding orbitals. If you see that the bonding orbitals are all occupied, suppose this is the original level of the atomic orbitals and these are unoccupied. So, this orbital is what is called the highest occupied molecular orbital, and this orbital is what is called the lowest unoccupied molecular orbital. And whenever reaction takes place with another substrate, so it is the HOMO of one, the highest occupied molecular orbital reacts with the LUMO of the other, because there cannot be reaction between HOMO and see there cannot be reaction between HOMO and HOMO, because that will not give any stabilization. So, it can only react with an empty molecular orbital. So, the interaction takes place between HOMO and LUMO. So, whenever another, I repeat, whenever another substrate comes, it has got a set of HOMO and LUMO. So, if it supplies the LUMO, then that has to interact with the HOMO of this, or if it supplies the HOMO, then it has to interact with the LUMO of the other system. Okay. So, it is a HOMO-LUMO concept, that reaction takes place by the interaction of HOMO and LUMO. Okay. So, now like here it is written HOMO of nucleophile interacts with LUMO of electrophile. So, when the nucleophile comes and displaces the chlorine, so it is this orbital which is the LUMO, because it is the lowest unoccupied molecular orbital, and then the HOMO, that the HOMO of the nucleophile that comes and donates electrons to this and interacts with this orbital. Okay. Best nucleophiles should have a high energy, this is HOMO, a non bonding high energy. So, the lower the gap between the HOMO and the LUMO, the reaction, the better is the situation. The lower the gap between the HOMO and the LUMO, the better is the situation, then the reaction will be more facile. Okay. I think so. Let us see again this in case of say SN2 reactions. Okay. In case of SN2 reactions, what happens? This is the nucleophile. Suppose this has this type of orbital, and it has got 2 electrons, and this is the CX bond. Okay. This is the CX bond. Now, what I am saying, that because it is now coming with the HOMO, so now it has to interact with the LUMO of this CX bond, the LUMO associated with the combination of carbon and X. Now, here it is what is drawn is the anti-bonding orbital, which is the empty orbital. First of all, as I said, that if this has also electron and this has got electron, then that combination will not lead to any stability. So, stability will come only when this is empty and this is filled, or the other way around. Okay. Now, in nucleophilic substitution, this is filled. So, the carbon has to supply an empty orbital in the form of the sigma star orbital of CX. Now, this nucleophile could have come from various sides, from this side or from this side, but yesterday I was telling that it will approach in a line along the CX axis, just opposite to it. Why it does so? Because that gives the maximum stabilization of the two orbitals. Okay. Now, this is what is called the stereoelectronic requirement. So, what is the stereoelectronic requirement of an SN2 reaction? That the nucleophile should approach opposite to the CX bond and along the CX bond. Okay. Opposite to the CX bond, that is true, and it should be along that CX bond axis. The approach should be along the CX bond axis. Why it is so? Because that ensures the stability, high stability of the transition state. See, when the interaction is taking place, that will be that will give the high stability of the transition state. As I said, stereoelectronic effect demands that the orbitals should be aligned in such a way so as to give maximum overlap, that means the maximum stability. So, that happens in the SN2 reaction. So, as it approaches, the carbon becomes the it gets a pure P form, and then there will be interaction between this, and this is this X is started to break away from this system. So, this is the transition state. In the transition state, the carbon is becoming trigonal bipyramid shape. Okay. It is partly attached to this nucleophile and this is partly attached to the X. Okay. Already there is started, the detachment has been started and the attachment is also taking place. Okay. So, new sigma bond and that is the old sigma bond being broken. So, that is the stereoelectronic requirement for the SN2 reaction, and after the completion of departure of X, this is the situation. So, this antibonding, this is now antibonding whatever was the sigma star orbital, the antibonding orbital was being offered, now that has after combination become a bonding orbital. Okay. And the other important thing that these three hydrogens were on these sides, on the left side, but now forming a cone, now they are after the reaction they have gone to the right side. So, they have formed a cone from the right side. Okay. That is important to notice. So, that is again reiterated there, that means the mechanism for SN2 is this is the transition state and this is the product. Okay. So, there is what is called an inversion of configuration, because if these three groups are different, then this has got an absolute configuration because X is also different. So, after the reaction it is again stereogenic center, but there is a earlier the X was on the right side and now the entering group is on the left side, and these three groups have been inverted from one side to the other. Okay. Has been inverted from one side to the other. Now, inversion of configuration does not mean that R going to S. Okay. That is very important, you should always notice this, that inversion of configuration does not mean R going to S or vice versa. It means that the bond formation takes place opposite to that of the bond breaking, which leads to the inversion. Okay. It does not mean R going to S, or it does not even mean that plus compound is going to a minus compound. Okay. Do not think that way. It is a change of configuration. Okay. Change of configuration from one to the other. That means, the incoming group is occupying the opposite side of the where the leaving group was. Okay. So, it is like you can compare this with this umbrella, that earlier this was this was the leaving group, and when the nucleophile comes, then it attacks from this side. So, this is the nucleophile bond, but what happens now, this whole portion has to be inverted. These are the three alkyl groups. So, that portion, no, that is not shown here, this whole portion, sorry, these are the things that is still there. So, that maybe that picture may not be very correct. I think the other way, the better way to do it is that if you have an umbrella like this, inverted umbrella like this, and if you do the reaction, so the inversion means, so this is X, now the Y comes and attacks this carbon. So, now this takes another inverted umbrella. So, this should be the picture, not the other one. I think other one has some difficulty. Okay. It does not really show the inversion clearly. It just shows that this is opposite to that. but this remaining the same, that should not remain the same, that should be in the opposite direction. Okay. Now, how do you know that there is inversion in the SN2 reaction? And there is a classic experiment that was done, that that the 2-iodooctane, this is 2-iodooctane, a plus form of 2-iodooctane was treated with radioactive iodide. Okay. So, what happens with radioactive iodide? The radioactive iodide will approach from the back side. Now, in this case the product is the same as the original, only this is radioactive and this is not radioactive, that is the only difference. However, if iodide comes from the back side, it will give a molecule which will have minus, which is the mirror image of this. So, this will have minus rotation and this has got plus rotation. So, suppose I started with 2 molecules of this and 2 molecules of plus compound. Now, if the iodide comes from the back side, if the reaction happens to only 1 molecule, then I have 1 molecule of minus compound and 1 molecule still remaining of plus compound, but that is what is called a racemic mixture. That means, the rate of reaction for each iodide incorporation, I get 2 molecules as a racemic pair. So, the rate of reaction is, so the rate of reaction is half of the rate of inversion, is half of rate of racemization. Rate of reaction is half of rate of racemization, because the racemization is happening at a double speed. Okay. For each 1 molecule getting inverted, you get 2 molecules being racemized. Okay. So, the rate of reaction is half the rate of racemization, and this was really proved. They checked the rate of iodide incorporation, that will tell you the rate of reaction, and they also checked the rate of racemization, that means the dropping of the optical activity, how quickly it is dropping. So, from that they figured out that it is exactly following that rule. Okay. So, that was a very excellent proof that rate of racemization is twice the rate of inversion. It is the other way of same thing, rate of racemization is twice the rate of reaction. 1 rate of reaction means 1 inversion, it is the same thing. So, 1 rate of reaction, I repeat, 1 rate of reaction is same as rate of inversion, because every reaction is associated with inversion. So, that is why you can say that. Okay. Now, so what happens in SN2, there will be inversion. Now, by the way, this inversion is called the Walden inversion, because it was Walden who first pointed out that inversion of configuration in an SN2 reaction. In SN1 reaction, what happens? The SN1 reaction, we know that there is formation of this carbocation, that is as the first step, the rate determining step. So, here what will happen? This basically leaves, and this happens only when this is a stable carbocation. Okay. Now, you have both the lobes are free. So, the nucleophile now can approach, it is the other, you can show it in the orbitals in the vertical direction. So, you have a 1/2 of the orbital here and 1/2 of the orbital in the down phase. So, but this is planar again, this is a plane, carbocation is planar. Now, if the nucleophile attacks from the top, so it will give this compound, and if you work out the configuration, it will turn out to be S, and if it comes from the bottom, then it will turn out to be R. So, what you will get is a racemic mixture of these 2 compounds. Okay. So, in SN1, in an ideal SN1 reaction, that what happens in an ideal SN1 reaction, there is complete racemization. However, what happens in many cases, there is what is called ion pair effect. So, this is what I have shown, that if this breaks and if this is completely free out of the leaving group, if the leaving group has departed a long way, then both the lobes are available for attack by the nucleophile. So, you get a plus minus mixture of these. However, so racemization is expected, extent of inversion is extent of retention, the same thing. However, due to ion pair formation, there is more inversion, than retention. What is ion pair? That means, this is now when it is departed, it is a plus carbocation and a minus the leaving group, okay, minus. So, now there will be some interaction still, electrostatic interaction, that may be present here, and so this may exist as a ion pair. If it exists as a ion pair, then this side is little bit blocked for the nucleophile to gain entry from this side, but this side is open. So, there will be nucleophile will have a preferential attack from this side rather than from this side, because this is little bit hindered. The hindrance is coming from the counter ion, that means the X minus of the ion pair. So, there will be more inversion than retention. So, in SN1 in many cases that racemic mixture is not obtained, but if there is more inversion, okay, and that is due to the, that signifies that there is a ion pair mechanism. Okay. Now, there are, I think I just skip these, we can come back to these type of problems. Okay, this is possibly quite interesting. I will not go to the mechanism. See, suppose I have a you know that in SN2 reaction there is inversion, but if I start with a chiral compound R1, R2, R3 and have a wedge, in many cases I may need to invert the configuration. That means, I need a compound where is exactly the mirror image of this. So, how to convert this into the mirror image? So, this is the inversion, but the problem is that I cannot actually attack this wedge by another wedge minus. So, there is no direct way of converting this into the mirror image by a reaction, not by another wedge. Okay. So, another wedge will not do anything anyway, even if it comes, you are ending up with a racemic mixture, you cannot get this compound. So, a one step or even a two step conversion will be okay. So, there is a very beautiful reaction which was called the Mitsunobu reaction. Now, there are ways to do it, that the ways to do it means you have to, but that will take many steps. See, you can convert into a good leaving group. First of all, wedge is not a good leaving group. So, it is very difficult to expel wedge by a nucleophile. So, in order to do that, you have to make it a good leaving group like O methyl or OTS. Okay. So, if you do OTS and then you now attack it with a nucleophile, so that this goes out and there is inversion of configuration, and this nucleophile should be such that it can be converted into a wedge without disturbing the stereogenicity of the carbon. So, you understood what I said. So, first convert it into a good leaving group and then add a nucleophile, suppose OCO pH, that means a benzoic acid, benzoate as the nucleophile. Okay. So, now the benzoate will attack from the back side and this will go out. So, the product will be now O and then CO pH. Now, if you can break this bond by hydrolysis without disturbing the stereogenicity of this, then you will end up with the inverted compound. In many synthetic operations, what we need at different stages is to invert the configuration of the carbon, and this is one way of doing this, and I will show you another way, that is called what is called Mitsunobu reaction. This is a quite modern reaction, that is why I brought this here. So, the problem is that if you have R, this is a chiral center, right, this is a chiral center wedge, and I want the opposite isomer. So, if the opposite isomer, that means the methyl should be alpha. So, what I did basically opposite isomer, you have to react, you have to put a benzoate kind of thing, so that this can be converted into wedge. Okay. This is not simple benzylation of wedge. If you do if you put the wedge, if you make the wedge to OCOPH, this methyl will remain the same. So, in order to make this, you have to convert this wedge into a leaving group and then attack that with a benzoate, so that you get this compound. Okay. Now, this is how do you do it? in one step. So, what you do here, there are you have to convert the weight into mesylate or tosylate. Instead of doing that, what you can do, this is a compound called diethyl azo dicarboxylate, DADE abbreviation, diethyl azo dicarboxylate, and triphenylphosphine is another compound. So, you add these two along with this alcohol plus the benzoic acid. So, what will happen? The triphenylphosphine will attack this nitrogen, the double bond breaks. So, it becomes N minus, and that picks up the hydrogen from the alcohol, your starting alcohol. Okay. So, the starting alcohol now becomes alkoxide. So, this is there should be a methyl here if you start from this compound. Then it attacks the phosphorus, phosphorus is now positive and oxygen has high affinity for phosphorus. So, this breaks. So, another anion is formed. So, ultimately you are having this RCH2O. If it is the methyl is there, then there should be a methyl here and then this phosphate. Now, what will happen? The benzoic acid will come from the back side, because this has become a very good leaving group. See, your ultimate objective is to make the OH a very good leaving group. Either in this case it was by methylation earlier, now it is by you are making a phosphoester, a phosphate bond, okay, a phosphate bond, and with a phosphorus positive. So, this is now become a very good leaving group. So, now the nucleophile comes and attacks from the back side and this breaks. So, that is shown in the next. So, now this opens up the nucleophile, that is the benzoic acid, goes to the this N minus abstracts the hydrogen from benzoic acid, that goes to the Nu minus, and then Nu minus attacks this from the back side. So, if it is a chiral center, that will undergo inversion. So, you get RCH, R carbon and Nu. Okay. If again I repeat, if it is a, if you start with a methyl here like this compound, then it will be the inverted compound with a benzoate here, if the nucleophile happens to be benzoic acid. So, this is a nice way, then you hydrolyze the benzoic acid and get to the OH. So, this is the Mitsunobu one step process of inversion. Here it is says one step process for ester formation. Yes, it is, it forms the ester OCOPH. So, one step process for ester formation, and there are so many reagents acting together here, okay, DADE, then triphenylphosphine and the nucleophile as well as the starting material. So, 4 compounds are reacting together, it is a high yielding reaction and you get the product. Another, now SN2 reactions lead to inversion, SN1 reactions ideally it should lead to racemic mixture, but because of ion pair formation, in many cases we see more of inversion than of retention, and there is some cases where there is complete retention of configuration that is possible. That is in case of where neighboring group participation occurs. Like you know that if a nucleophile is already present in a molecule like this, the sulfur, and you are trying to kick out this chlorine with an external nucleophile, then before the external nucleophile comes, the sulfur attacks this carbon from the back side, and so you get this sulfonium ion, but this is not a stable compound. So, now the nucleophile, the actual nucleophile, if it is water, comes, attacks the carbon, attacks one of these carbons, these two are identical, and then breaks the these two are identical, say these and this. So, it can attack here or this can attack there, these two bonds are identical. So, if it attacks here, then this breaks and the product is ultimately OH. So, it is not a direct displacement of chlorine by chloride by OH, but rather it is a assisted replacement. So, this is called neighboring group participation or ankymeric assistance. Now, when this ankymeric assistance takes place, you have to be, then there is a question of retention of configuration that can take place. So, this example will tell that if you take alpha bromo propionic acid, propionate form, okay, means alpha bromo propionic acid, you add dilute OH, a dilute sodium hydroxide. If you add dilute sodium hydroxide, what happens? This will be O minus now, and dilute sodium hydroxide means there is a lot of water and less of OH minus. So, what happens before the water as the nucleophile or OH minus, but which is present in much less concentration acting as a nucleophile. Before that nucleophile comes, you have a nucleophile, inbuilt nucleophile here, O minus, and that now attacks, that can attack the carbon. So, make an SN2 displacement on the bromine, and forming what is called a lactone. Okay. First, what is that is in the next slide. So, what I am saying that this can attack the carbon and bromine expels. So, there is an inversion at this configuration. So, that is inversion 1, then OH minus whatever is there, much less concentration. So, that is why it took so much time, it was waiting for this lactone to be formed. So, once the lactone is formed, this is called alpha lactone. So, it comes and attacks this carbon, and this carbon oxygen bond again opens up. So, this is another inversion. The result is that you have displaced the bromine with a OH. So, result is the alpha hydroxy carboxylic acid. But in this case, if the mechanism is via this it is a two-step process via this neighboring group participation, then the overall product will have the same configuration S configuration. Actually, there is no inversion of configuration. However, as I said, inversion of configuration does not mean R go to S or S goes to R, but here, because that depends whether S will remain as S, that depends of the priority of the departing group, whether and the priority of the incoming group, whether they are same or not in the final product. So, here bromine is number 1 in this which is attached to this carbon, which is also number 1. So, that is why this is S and that still remains S. Okay. But do not be confused, there may be cases if suppose this is replaced by a carbon, then that inversion of configuration takes place, but the that rotate this R, then S will become R, because the priority matching will not be there. So, there has to be priority matching if S wants to remain S or R wants to go to the R. So, this happens with dilute NaOH, remember. If it is concentrated NaOH, then before this anion can attack to this carbon, because of the high concentration of OH minus, is directly attacks to this carbon and replace the bromine. So, that becomes the inversion. Okay. So, that is the inversion case. Okay. So, it can be inversion depending on the concentration. For low concentration, there is this ankymeric assistance followed by alpha lactone and then breakage of the alpha lactone. In that case, the S remains S. Again I repeat, S remained S because of the same priority OH has as the bromide had in the original compound. Okay. But the best thing is that there is retention of configuration in ankymeric assistance reactions, assisted reactions, and there is inversion of configuration if it is a direct displacement. Direct displacement only happens with concentrated alkali. Okay. This is the same example, but you have to see this says that two products. Okay. This is we can take it up very quickly before we finish this part. See, what was the problem? That S Me and this was a chiral center CH3 and a hydrogen, okay, and a Cl. So, that was the product, that was the starting material. So, if you now do the reaction trying to displace with OH minus, suppose. So, before OH comes, there will be ankymeric assistance, okay, the chlorine leaves. So, now you have Me and so there will be inversion here. So, there will be methyl on this side and this side. This is the case, sulfur is now plus. Okay. Now, it says two products. Why two products? This is hydrogen. So, now the nucleophile can attack this carbon and opens this up. This is path A, suppose, or the nucleophile can come and attack this carbon, and that is path B. So, if it is path B, then the product, in the product there is retention of configuration. This is important. So, suppose path B product is what? Me, and then there is a CH2, then this, and then you are again back to the this is the hydrogen and this is the OH and this is the hydrogen. So, this is the product in path B. So, this configuration is inverted. Sorry, it is a retention of configuration, because it has undergone two inversions. One is here when this attacked. So, one inversion here and then another inversion here. So, overall this is retention. However, if the wedge attacks at this carbon, which is most likely to be, because this is CH2 versus a tertiary carbon. So, if that attacks, so path A, that will give SME and then CH2 OH, CH2 SME, and then you have this CH3 hydrogen, then CH2 OH. Okay. This is the product. Again I repeat, if path A, so this is attacking here, this is broken, and if this breaks, then you have CH2OH, then this stereogenic center, then this sp. So, what happens here now? Interestingly, the inversion, there is no question of inversion or retention at this carbon, because this is not chiral center. So, whatever inversion has taken place, that remained. So, now you have only the inverted product. Okay. Now you have only the inverted product. So, depending on where it is attacking, do not think that in all anchimeric assisted product there will be retention of configuration. It depends on where the nucleophile is attacking. If the nucleophile is attacking the same carbon where the anchimeric assistance has taken place, then there will be retention of configuration. But if the nucleophile is attacking at a different carbon, like here in path A, then the inversion of configuration retained, that happened in the anchimeric assistance. Okay. I think that is clear. So, we end here about this SN1, SN2 and this neighboring group participation and the associated stereochemistry. Thank you.